Hello, welcome to CSC 351, Introduction to Data Science. Today's topic is on covariance and correlation analysis, two important statistical measurements which we are frequently using in many data science problems. So we start by talking about covariance, and then we will show that how covariance and correlations are related, and then I'll give you some examples, and then at the end we show how we can compute covariance and correlation in using scientific libraries in Python. It's very important to have a very good intuition from covariance and correlation. So in many data science problems, and also in particular in machine learning algorithms, when you deal with the probabilistic and statistical pattern recognition, understanding of covariance matrix is crucial to know how data behaves, how data are related. So computing covariance and correlation is easy. You have a vector or a matrix, you pass it to a software, and that will compute for you what is the correlation or covariance. But what is important is to understand and have an intuition with the number you obtain, what's the interpretation of this number. So pay attention to these slides. I try to provide intuitive understanding of covariance and correlation. So what is covariance? Imagine that we have a vector, we call it vector x. As I said, we use an arrow on the top to denote that this is a vector, and this vector has some elements, and all these elements are random variable. That means they have drawn from a distribution with a known probability. So this is one instance of this random vector with the element x1, x2, xn. And then we can imagine these are different features we have collected, and then we wanted to investigate the relationship between these features. So in particular, let's say I'm interested to see if I have the value for x1, and then if I increase the value of x1, I wanted to know if, let's say, x3 increases or x3 decreases, or there's no x3 doesn't change at all. So we are looking for statistical measurements that gives us the relationship between two random variables and show us how these random variables are interact with each other. If increasing one, decreasing one will influence the other one, or no, they have nothing to do. A very famous example, we're all interested to predict what is the stock market value. And then we are looking for some attributes that by which we can predict the stock market values. Let's say if I wanted to see if the oil price is related to stock market. So if I call x1 the oil price and then x3 as a stock market, then I want to see if the gold price goes up, how would the stock market behaves, go up, down, or no change. So covariance between two random variables is a number, scalar number, that shows that how these two values interact. High value for covariance shows that their interaction is positive. We can also have negative values, and also covariance could be 0. That means these two random variables, they don't interact at all. But usually we don't have only two random variables. We have an array of random variables, and we wanted to investigate the covariance between each pair drawn from these vector. So if I wanted to have, if I call the covariance as, let's say, for the as short as cov, so ideally I wanted to have the covariance between ith element and jth element of this vector. So therefore, if I wanted to have all values, covariance can be represented by a matrix, right? By a matrix. So I can say the covariance of X is a matrix, and then with the element of covariant between x1, x1, and then the second column is covariance between x1 and x2, and then the last one is covariance between x1 and xn. And then the second row and the last row of this matrix would be covariance between x1, xn, and x1, and then this cell in this matrix would be xn and x2, and then all the way to the last element in this matrix, covariance between xn and xn and xn, right? So as you see, the covariance of a vector or n random variables can be represented by a matrix whose elements show the covariance of a pair. We also note that covariance matrix is also always symmetric, meaning that the covariance of xi and xj, where I and j's are the index of two arbitrary elements from vector x, is always equal to the covariance of xj and xi. This is important because one of the characteristic of the covariance matrix is that this matrix is symmetric. So all elements x and I equals to x, j, and I. That's another properties. So then if you compute the covariance matrix, we can go for each element to see how changing a value for one random variable will influence the other one. We also note that the covariance matrix for on the main diagonal, namely covariance of xi and xi, is equal to the variance of xi. So if you wanted to compute the covariance for an element with itself, it's equal to variance. So all elements on the main diagonal of this matrix, they are basically variance of each individual element. So basically this is equal to the variance of variance sigma 2 squared, and this is sigma n squared, right? So this is what is a covariance matrix. So if you give you a vector and we say this vector is a random variable vector, then if we wanted to see how the elements are we need to compute the covariance matrix. Okay, so then how we can compute the covariance matrix? What is the formula? As I said, we have two types of covariance: population covariance and also sample covariance. So as I said, in statistic, we have a population for which we have some parameters. These parameters are namely a mean or variance or other sufficient statistics that represent these population. Usually these sufficient statistics are unknown. Therefore, we do the compute the sufficient statistic from the sample population, where we have collected or drawn some sample from this population, and then we can compute the sufficient statistic. One of them is covariance matrix. So if you wanted to compute if you have access to actual mean and the probability distribution of the population, and if you wanted to compute the covariance matrix for the population, this is the formula for computing the covariance. So covariance of vector x, which is basically a matrix of dimension of n times n, because we want to find interaction between all elements, and we know that this matrix is a symmetric matrix, is equal to expectation of the vector minus the mean of vector times vector minus the mean of the vector transpose. So when we wanted to compute covariance, and also we wanted to compute the correlation later on, what we need to do first, we need to center our data. So, or also we call it d-mean our data. So d-mean or centering the data means that we subtract the mean from each value. So in this way, we basically shift the mean to the origin. So we do the same thing here for vectors. So we first compute the mean of vector x. Note that when we say we compute the mean of vector x, that doesn't mean we compute the sum of the elements of this vector divided by the number. No, that means we are computing the mean for each element of this vector. So therefore the mu is a vector which is equal to the mean of the first element, which is this one is a scalar, mean of the second element, and all the way mean of the last element. How to compute this mean? That means you need to have some samples drawn from the population. These samples are vectors. These samples, the dimension is 1 times n. And then x is also vector, you can do this subtraction. So first of all, we need to center the data. So this process is called just centered data. That's important. And also we know that this t denotes the transpose. If you multiply this vector by this vector and then take the expectation, then we will have the covariance matrix. But in many cases, we don't have access to underlying population. We only have some samples. Therefore, we're only able to compute the sample covariance matrix, which is much simpler. And also, we know that why the output of this product is a matrix, you can convince yourself. Let's say if I have a vector of dimension n by 1, and then multiply this one by a vector, I have dimension of 1 times n, 1 times n, then the resulting matrix is n times n. Okay, so in here x minus mu is n times 1, because vectors are column vectors, and then transpose of that vector is a row vector, and if you do the multiplication, you will get the an n by n matrix. Okay, so what is the sample covariance? So let's say we have m samples drawn from the distribution, m samples drawn from this distribution. Then what we do, just basically for each sample we compute this. We first, for each sample, we decenter we center that sample or d-mean that sample, meaning that we subtract the mean and then multiply it by transpose of the vector that gives us a matrix, and then we sum up all these matrices and then we divide each element or each cell in this matrix by n, or by sorry, this should be m. I made a mistake in here, so this should be m, by number of samples. And then we divide this one by m, where m is the number of samples. So we have two dimensions here. This is very, very important. I have seen many students, they make this mistake. So one is the size of samples, another one is the size of feature space. So you should be able to distinguish between these two dimensions. So how many samples do we have in here? We have m samples. We have m samples, and each sample is a vector. What is the dimension of that vector? The dimension is n. Dimension is n. So therefore, we need to divide the covariance by m. At the end, the covariance would be, the sample covariance would be a matrix of dimension n times n. So what is this process? This process basically, after you multiply these two vectors, you get a matrix, and then you sum up these matrices. So each of these matrices is n by n, n by n, n by n. And then we sum all of them. So this is the first matrix, 2, and then this one is mth sample. And this one is also n times n. And then we sum them element-wise, element by element. And then the resulting would be a matrix, which we later on divide each element by m. That gives us the covariance, sample covariance. Usually we compute the sample covariance for the data. And also we should note that when we are talking about covariance matrix, we have this assumption that data are normally distributed, and this is an assumption that many times we usually don't forget or don't mention. However, according to the law of large number, then we can show that for any other distribution, the covariance converges to the sample covariance. So that's how we compute the covariance. It's n by n. So this is a covariance matrix. So let's now consider some data, and I wanted you to think, how do you think that the covariance matrix looks like for this data? So for the figure on the left for this figure, we have some two-dimensional data. So in here, vector x, which is a random sample, has two elements, let's say x1 and x2, x1 and x2. So this is our vector. And so then these are some random samples drawn from the distribution. So we had access to this data. So the scatter plot, so this plot is basically a scatter plot where on the x-axis I have x1, and then on the y-axis, let me draw a solid line. The y-axis, I had, this is x2. So for each sample drawn for this distribution, we can have scatter plot. For instance, this guy in here, this is the point, this is scatter plot, this is the value for x1, and this is the value for x2. So for all samples, if you plot them, we have these scatter plots. So what is the covariance covariance matrix in here, and what is the meaning of this covariance matrix. For this case, the covariance matrix, basically covariance of vector x is a 2 by 2, because this is 2 by 1. The number of features or dimension of feature is 2, therefore we have a covariance of dimension 2 by 2. And then we have in here the first element is basically the sigma on x1 squared. This is variance of x1. This element is x2, and this one is covariance between, so let me have a bigger matrix to show. So this one is covariance between x1 and x2, and this one is covariance between x2 and x1. We know that they're equal, and this one is variance of x2. So this is how the covariance matrix for this data looks like. So what do you think? What are the covariance matrix for this element? In particular, I am interested to see what is the covariance between x1 and x2, this value. So we see that there is no meaningful relationship between x1 and x2, right? So we cannot say if x1 increases, x2 also increases. For instance, if I say, okay, from here, if I increase the x1 for this sample, goes to x2, but for this sample, if I increase the x1, x2 will be will decrease. So for this one, there is no relationship between x1 and x2. Therefore, what I expect to get from this data has some variance. So I would say this is, if data are normalized, then the variance is 1, and then covariance between x1 and x2 is 0, and then also the variance. So if this is unit 1, we have 1 unit. So this is unit minus 1, this is 1, plus 1. This is also, if this is plus 1, and this is minus 1. So for this type of data, when we have like a sphere or a circle, the scatter plot, this type of the covariance is always the between two values is 0. So here we talk about the two-dimensional data. So that means there is no relationship between each individual element of this vector. So later on we will talk that means these elements are uncorrelated, or correlation is 0 between these elements. So whenever you plot the scatter plot of data in 2 dimension, if the scatter plot looks like a sphere or a circle, that means that this data, the data are uncorrelated. On the other hand, for the figure on your right, so for this one, we see that if I increase x1, then x2 also increases. And if I decrease x1, then x2 also would decrease. So that means that this x1 and x2 somehow interact with each other. So, I should correct myself. If I increase x1, then x2 decreases. And if I decrease x1, x2 decreases. They have the opposites of each other. So then, so that means the interaction is negative. So they interact. The covariance matrix shows that they interact, and this interaction is -1. because increasing x1, x2 decreases, and also if we decrease x1, x2 increases. So you see that this is important. When you have the value of covariance, you can get a lot of information about data you have. In particular, this data are some measurements from some phenomena. We have collected the data and we want to see how the data are interacting with each other. For instance, if you have, this is a scatter plot of, let's say, the grade of a student, so this is, let's say, x1 is number of times students watch TV, and then x2 is the grade, so they are negatively correlated. That means if I increase x1, then the grade decreases. So we can have a scatter plot, you can compute the value to have a numerical value to show how these data influence each other. So that's basically the meaning and some intuition about the covariance matrix and what each element in covariance matrix means. One of the important things about covariance is its relationship with independence. So we know that we're talking about the random variables. These are some data drawn from some distribution. So these data have some probabilities. We know that if two random variables, let's say x1 and x2, are independent, then what will happen, the joint probability is equal to the product of the probabilities. So px1 and x2 equal to px and y equal to px times py. So if two random variables are independent, then the covariance between these two random variables is zero. However, if the covariance is zero, then we cannot say these two random variables are independent. So that's extremely important to note, this one and this one. Independent note that the covariance is zero, or correlation is zero. We can also extend it to correlation, but other way around is not correct. That means if the covariance is zero, then we cannot, they are independent. One reason is, first of all, the covariance shows a linear relationship between two random variables. Therefore, it doesn't reflect exactly the causation between two random variables. So I give you an example in here. So let's consider this scatter plot. So let's consider this scatter plot. Okay. So then we have this data. This is the random vectors. Each point is a sum. So for this data, the covariance is zero. They're not related to each other. So for this data, we know that for this data, so if this is x and this is y, the covariance between x and y is zero. But these data are dependent on each other. These data are dependent. So that doesn't mean that p x and y is equal to px times py. Why? Because we all know this data follow a parabolic like this, right? And then for this case, y is equal to x2. They're dependent. they're dependent on each other. If I have x, I can also compute y, and if I have y, I can also compute x. They are dependent on each other, but the covariance, or if I say correlation between these two random variables is 0, because correlation, the covariance shows how they are linearly related to each other, whereas for this type of data, they're non-linearly related to each other. Correlation does not capture the relation. This is very important. Sometimes we compute a correlation and then we conclude there's no relationship, but we should have in mind correlation is only valid for relationship that are linear. So linearity means that if I have x1, and then linearity means that if I have x, then y is the output of this process, multiplying x by a scalar and then shift it with some value. This is a linear relationship between x and y. Okay, so now having a good understanding of covariance, we can easily introduce correlation. So correlation basically is a scaled version of covariance. So as you see, for covariance, sometimes let's say we wanted to compare the correlation between x1 and x2 and x3 and x4. So if the value of x1 and x2 are large and the value of x3 and x4 are small, then the correlation between, because then covariance is related to the magnitude of values, then the covariance between x1 and x2 might be much larger than x3 and x4. The reason is we need to somehow compensate or normalize our data by their magnitude, how much they spread. Therefore, basically, correlation, again, correlation basically shows a linear relationship, how the direction of the linear relationship between two random variables. So in here, when we wanted to compute the correlations, we only consider two random variables. We don't consider a vector, even though we can also define the correlation for each pair of a vector, but now we've only focused on two random variables drawn from two distributions. They might be identically distributed, or they may have different distribution, but the assumption for the correlation is the data are sampled from a normal distribution. So then correlation, we usually use this rho. This is a Greek letter. If you want to compute the population correlation coefficients, we usually call it coefficient, correlation coefficient. It's equal to the covariance of x and y. We already know how to compute the covariance, and then we divide by the standard deviation of x and a standard deviation of y. Or in other words, the correlation is expectation of x minus mu. It should be also transposed in here. And then y minus mu y. These are the mean of this vector and mean of this vector. And then divide by the variance. So this is variance of x and this is variance of y. So we also have the sample correlation coefficients. Basically for that we compute the sample covariance and divide by sample variance of each value. So this is, we already know what is this. This is the sample covariance, and this is the definition of variance, and this is the definition of variance. So as you see, the correlation coefficients are related to the covariance. They're basically covariance values, but we normalize them by the variance of each random variables. Namely, if we want to compute the correlation between two random variable xi and xj from a vector. We compute the covariance of xi and xj, and then we divide by variance of xi and variance of xj. Okay, so this is how we compute a correlation, and we usually don't compute a correlation by hand. We have some scientific libraries that they compute the correlation for you, but what is important to understand what the numbers you get from a correlation analysis mean and how to interpret them, and how to have a good intuition about these statistical measurements. So there are some attributes of correlation coefficient. So correlation coefficient, if we call it rho, is always rho is always greater or equal than -1 and smaller or equal than +1. So basically, when we normalize the covariance, we bound it between -1 and 1. So then what does it mean if you get a value for -1 for a correlation? So that means there is a perfect negative relationship between data. If you get 0, that means they're uncorrelated and there's no relationship, linear relationship between data. That's important, that correlation and covariance only show the strength of linearity between two random variables. As I mentioned in previous example, the data might be related in a non-linear manner, so then correlation and covariance cannot capture that. If you get a +1, that means a perfect positive relationship between values, and then they have the meaning is that means if you increase x1, x2 also increases, or they are in the same direction. So namely, if I wanted to show a plot, so if I have, let's say, this Cartesian plane, so the data will look like this line. Basically, this line show a perfect correlation. So if let's say if this is x1 and x2, they are related through this line, then rho for this one is +1. And if they are negatively correlated, then we have this line. So for this one, rho is -1, right? So that's a correlation. So whatever we said about covariance also is true about the correlation. If the correlation between two random variables is 0, that doesn't mean these two random variables are independent. But if two random variables are independent, the correlation between two random variables is 0, because these data, they are not related at all. And then when you have the scatter plot, you are supposed to get a center isometric cloud or a sphere or a circle type scatter plot for when the data, the correlation is 0, right? So property of correlation coefficient, as I said, this is between correlation coefficient is between -1 and +1. Correlation coefficient is independent from the change of origin and scale. That means if you have two random variables, they are correlated. If you change them, or if you sum a number, then the correlation remain the same. That means if the correlation, let's say correlation between x1 and x2 is equal to like alpha, then the correlation between x1 plus b and x2 plus b is also alpha. That means they're change of origin and scale, they are invariant to that. So also the correlation coefficient is a geometric mean of two regression coefficients. So the geometric mean of two random variables is the square root of their product. We talk about that when we will talk about regression. As I said, the relationship, we assume the relationship between two random variables is linear. Also, one important thing about correlation, when you compute the correlation using the given formula, the value of correlation may be impacted by outliers. So one of the cons of the correlation, computing the correlation coefficient using the formula I gave you, because we can also compute the correlation coefficient using two other different formulas, which I'll give you later. But if you could use the typical way of computing correlation coefficient, which is called the Pearson correlation coefficient, has affected by the extreme value of outliers. And also sometimes when you have lots of random variables, then it's a very time-consuming process. Imagine you have a vector of dimension 10. So let's say we have an x, which is vector belonging to R10. And then if you wanted to compute the correlation between each two random variables, then you need to compute the correlation coefficient for choose 10, which is and lots of computations. As I said, when you wanted to investigate two variables are related and you have samples, the best way to first have a prejudgment about data is to have the scatter plot of data. So scatter plot, when you have two random variables and you have samples, then you can have random variables for each point of x1 and put it on x-axis and x2 on y-axis, and then have the scatter plot. So scatter plot basically provides you a very good visual insight about the data, and you can do some inference or results about this data. Namely, we can somehow guess what the correlation coefficients look like, or these data are related or not. So in here, we have a number of different scatter plots from the random variables drawn from different distribution with different relationship, and then on top of each one you have a value which is the correlation coefficient. So these values are correlation coefficients. As you see, for this data, the correlation is 1. For this data is on. For this data, which I said that they look like a sphere, a circle, this is a correlation is 0. And then if the direction is flipped with respect to the y-axis, the correlation is negative, and here we have the perfect negative. So these are some other cases about negative correlation, and we see some cases that the data are dependent, but the correlation is 0, similar to example I showed previously. So this data correlation is 0, but these data are not, they're dependent. So we cannot say px and y is equal to px times py. So they are dependent. So they are dependent but uncorrelated. Okay, so this way scatter plots can provide some visual understanding how data are related. Here I'll give you an example. When we are dealing with the correlation and when we are dealing with the covariance or computing the correlation, as I said, If you compute the covariance, if you have a covariance matrix, then computing the correlation is extremely easy because you already have the values. You just need to divide by variance. That's easy. That's easy. So let's say we have given this data, this matrix, and we are asked to compute the covariance matrix. So also we can compute the correlation coefficients, right? So first of all, when we are given this matrix, how we going to read this matrix? How we are going to interpret this matrix? So basically, we have some rows and we have some columns, right? What are rows and what are the columns? So rows in here are samples, and columns are different features of this sample. So in fact, in here, what we have a sample we call x1, and this is x2, and this is x3, and this is x4, and this is x5. So n in here is 5, number of samples. Each sample is a vector of dimension 3, right? So if you put it together, that would be a matrix. That would be a matrix. Now, if you wanted to plug these values into the formula, then you should be able to read it. So if I give this one to many students, they get confused. What is x in here? What is row? What is column? What is sample? So I was supposed to multiply x by x transpose. And also, as I said, we need to center the data. So how to center the data? We need to compute the mean of the vector. So if you want to compute this mean of this vector, so because we need to compute the sample mean. For sample mean, for first elements of this vector, we have 1, 2, 3, 4, 5 elements. So we sum them up. We sum this value and divide it by 5. So if you wanted to see what is the mean for the first element, so we have 5 elements, three features, and then mu1 is equal to 4 plus 4.2 plus 3.9 plus 4.3 plus 4.1 divided by number of samples, m, which is 5. And then that gives you 4, 1, 10, this value. Okay, you can compute the other values the same. So then after you center the data, that means for each vector you subtract the mean and then you do the calculation. So that means I show you, so this is basically if I wanted to compute the covariance for these, the covariance would be the covariance x is equal to 1 over 5 because I have 5 samples. Then I have a big bracket here. In here, I need to multiply the x1 minus mu times x1 minus mu, but this one should be transpose. And then we continue all this to x5 minus mu times x5 minus mu transpose. Okay, and then divide each value by 5. At the end, we get a covariance matrix of 3 by 3. 3 by 3. 3 by 3. Which is here, this is a covariance matrix. Now we can basically investigate what is the relationship. So these elements on main diagonal basically are variance. They're variance of x1, x2, and x3. So, and also the matrix is symmetric. As you see, these values are equal. These values are equal. So that means this matrix is symmetric. And also now we see that there's a very small correlation or covariance between these elements. For instance, the x1, this is x1 is related to x2 more than x1 related to x3, right? Because this number is smaller than this number. Or if I change the x1, if I change by x1, I mean the first elements. The second element will change not that much. So this is how we compute the covariance. If we wanted to compute the correlation, then we need to divide this by the variance. For instance, if I wanted to compute the correlation between x1 and x2, then this is equal to the covariance of x1 and x2, which is equal to 0.75, then divide by variance of each x1 and x2, which is 0.25 times 0.0070, right? So that's the basically how we compute the, and then we need to take the root of this. The root of this. So that's how we compute the correlation. So so we can get a number out of here. So this is basically 75 times 10 to the power of minus 4, and this one would be 25, which is 5, and then square root of 7, and then what comes out of this one is 3 and 3 minus 6. This is 10 minus 3. So that would be the, so this one also cancel out. This is 25, and 25 divided, so the covariance between these two would be 25 divided by square root of 7 times 10, or 2.5 divided by 7. So if you compute that number, that would be the correlation. Okay, so I would encourage you to spend some time, even though you will use software, but working through this example by a pen and a paper, using a pen and paper, I will let you to understand the correlation and covariance forever, and then that also helps you to recall how to compute the correlation and covariance. As I said, so far, the method we used for computing the correlation is based on the formula called Pearson correlation coefficient. As I said, there's a problem with this way of computing correlation. First, this correlation coefficient is very sensitive to outliers, and also the second assumption is when we are computing the correlation using Pearson. So these are the name of 3 scientists who basically first came up with these methods of computing correlation. So also the Pearson correlation coefficient assume that data are normally distributed. There are 2 other methods. One of them is Kendall, and another one is Spearman. They are non-parametric correlation techniques. That means there's no closed formula for that. There's no parameters we can compute for them. They are based on rank of the data, and they are extremely useful when you have dealing with the ordinary data, or when data are drawn from a multinomial distributions. So let's say like we have some categorical data. For categorical data, it is much better to compute the correlation coefficient using Kendall or Spearman. And then there's also no assumption about the distribution of underlying random variables for which you wanted to compute the correlation. When you're in Python, you can easily use all these two correlation coefficients. And then the last point I wanted to mention is how to compute the correlation using scientific libraries in Python. You can use the SciPy, and from SciPy, from stats and stats library, you can import a Pearson, and then if you have a vector, then this is the vector x and y. You can compute the correlation between these two vectors. So there are a couple of points in here I would like to mention. So about this question mark is this question mark in here. Basically, if you have a function or attributes or method in Python and you wanted to get some help about this function, if you put the question mark before that and then run the cell, then that will print out the help function for this. That gives you some information about the Pearson input output attributes of that function. So that's nothing in here. The second one, when you're computing the Pearson correlation, there are two outputs. The first one is correlation. The second one is a p-value. So p-value is a statistical measurement that gives you the significance of the correlation you obtain. So if p-value is not significant, even though correlation coefficient is high, that doesn't necessarily means the statistical results are significant. Hopefully we'll have time about talk about the hypothesis testing and p-values, but if you're using the Pearson correlation coefficient or other type of correlation, and they also print out a p-value, the p-value is basically shows the significance of your experiments. This experiment is significant or no, how much I can rely on my results. So I can say the correlation coefficient for this data is 1 with 100% confident, or I can say the correlation coefficient is 1, but my confidence is 50%. So p-value shows that correlation. And the lower is the p-value, the more the results are more statistically significant. So if you have a p-value of 0, that means the results are perfectly confident. But if the p-value is smaller, then that means the results are not significant. Usually the p-value smaller than 10 to the power minus 2 is very significant. Another way of computing the correlation is using NumPy. You can use NumPy library. In here we generate two random vectors. This is this rand_int, that means this will generate random vector from the 1,000 samples from interval of 0 to 50, and then that will add another 1,000 samples, and then we'll add a number from interval of 0 and 10. So this is the second one. So we expect that these x and y to be correlated. Why? Because the y is equal to x plus a random noise. And then we can compute the correlation coefficient from NumPy library, and also we can plot it. This is the scatter plots. As you see in these scatter plots, the data are positively correlated. That means, as you see, the correlation in here between x and y is 0.81, which is significant. And as you see, that means the direction of change is in positive. If you increase x, y also will be increased. The reason, as I said, basically y is x, but we add some random noise. Also, it's good to get familiar with these functions, these random generator functions. One of them is rand_int, so it has 3 inputs. That means goes and generate 1,000 samples from this interval, go and generate this one random normal, that will generate some normal data with mean 0 and variance 1 from this interval, and that there you can specify the number of samples. And this part is for the matplotlib. If you wanted to plot data or 1D, 2D or different type of data, you are using this data. And then if you want to use the scatter plot, this function is for plotting the scatter plots. And then if you wanted to have your plots grids, then you use this function. So I will upload some slides on just visualization technique and briefly talk about different methods of visualization, but there are tons of nice tutorials about visualization techniques. As I also, you see the correlation between a value and itself is 1, because a value is 100% correlated to itself. So I have also uploaded the Jupyter Notebook files accompanied with these slides. So please upload them and run the codes and then change the value to get a sense how to compute the correlation, and also to get a sense by looking at the scatter plot and also the correlation coefficients to see how you can interpret the results. That's, as I emphasize in here more and more and more, it's important you can get this skill and mastery that you can have an intuition about the results you get, and also you can have an interpretation. Only getting your codes run and print out the number without understanding what this number means, and then if you tweak a little bit the output, how will change the if you change the input, how would change the output. Then if you don't have any intuition, then you cannot probably use these tools for apply them to a real world problem and then make it better. So this is enough for this video. So in this video we talk about the covariance and correlation, and then intuition behind them and how to calculate them, and property of correlation and covariance and how they're related, and also relationship between covariance and also the independent random variables. In the next lecture we will continue these topics and go to principal component analysis, which is a topic which will combine the linear algebra with the statistics, and then we introduce a technique for dimensionality reduction. So wish you all a good day or night, and please stay tuned for next video.